The first time that you encounter divergent series in physics and you give them a finite value, you might be like, what's this? Is this some kind of magic? In reality, it takes some time to digest that. Because when you, for example, consider the Casimir effect, you start from a divergent series. And one thing that you can do is to regulate, quote unquote, regulate the expression, the series. And there is also an integral. But when you regulate the expression, for example, you can introduce a decaying exponential. So when you let a certain parameter, epsilon, go to zero, you will get back your divergent expression. What is the advantage of this? Well, the advantage is that you can separate the divergent part from the actual important finite part. Long story short, you can calculate the integral and the series in this way, and what you find is the energy per unit area, but you find it as a sum of two terms. One term is the finite part, whereas the other term is dependent upon the parameter epsilon, which goes to zero, and it is some power of 1 over epsilon. So as epsilon goes to zero, you will get that that term will diverge. So what's the point? You still have the divergence. Well, actually in this case, when you separate these two parts, this is very interesting, because the force, in the case of the Casimir effect, is a difference of the energy. Why am I saying difference? Well, because you have to calculate a derivative. So a derivative is some kind of difference after all, right? But when you take the derivative, and in this case you are taking the derivative with respect to the distance between the two plates in the Casimir effect, since the divergent part does not depend on this distance, it's a constant with respect to the derivative. So you're going to get zero. The divergent part is going to give zero. And you're just left with the finite part. So the force will not be divergent. The energy is divergent. But the important thing to understand here is that the divergent part in the energy is not something that's physically measurable. What you can actually measure is the force, as in the Casimir effect. There are other examples, and of course there are also other regulators that you can choose, not just the exponential type. But this is something very general that could let you understand much more deeply this so-called regularization, fundamental topic in QFT, quantum field theory.